guys, my name is Kevin Gima, and I investigated the question, are PVT nanowires ideal thermoelectric materials for semiconductors? Alright, so first I'm going to basically give an introduction to the basic concepts so you guys can understand my research better. Alright, so basically the thermoelectric effect, what is it? It's basically converting temperature differences to electrical voltage. And then the thermoelectric material is basically materials that exhibit the thermoelectric effect, and we basically make these types of materials by doping, which is adding impurities to various metals. So for my research, I investigated 2 PVT nanowires, which were doped with iodine, 2 were doped with sodium, and the remaining 2 were undoped. And then also 3 of these nanowires have a rectangular structure, and the last half has a helical structure. Okay, and these are just examples. So this is a helical structure doped with iodine. Bottom is rectangular structure doped with sodium. And then now, just a brief recap as to the methods that I used for my research. All right, so basically, I did density of states for all 6 of my models, and density of states is the number of states per interval of energy, and it's basically defined as a summation of all these delta functions. Absorption, it's basically oscillator strength that is defined as the probability that an electron that absorbs a photon will shift into orbitals, and these are all the relevant equations that go with that. Okay, now for the meat of my presentation, which are the results and analysis. Okay, so the first thing I have here is momentum dispersion, band energy on the y-axis, momentum on the x-axis. As you can see for graphs B, C, D, and E, they're mostly horizontal. So that basically means there's a minimal dependence on the band energy with the momentum. However, for graph A, you can see that there's a strong linear dependence of the band energy with the momentum. And if I had more time, I would investigate that. And that's one of the questions I plan to investigate going forward into my research. Okay, and this table here is my density of states. As you can see here, the 2 undoped graphs here in this column have the smallest band gap, and then the Na doped nanowires here in this column have the largest band gap. The I doped helical has the smallest band gap. And for this one, I know like this isn't the right graph because it doesn't have the HOMO and LUBO orbitals. So I apologize for that. But since I was running out of time, I just wanted to show you guys what I did for this. So again, I know it's quite right, and I'm really sorry about that. Okay, and these are my absorption spectrographs. So in terms of time, I just wanted to briefly show you guys this, and I'm not going to go over them too much in this presentation, but if you guys have any questions about this, you are welcome to ask me. Alright. Okay, now for the conclusions. What conclusions can we draw from my results? So to recap, the purpose is to find out if PVT nanowires are good materials for semiconductors. The absorption spectra, density of states, and momentum dispersion for 6 of these models were calculated. So it appears from my all the research I've done that the sodium doped PVT nanowires are the best material due to their band gap. However, more work is needed. So if I had more time for my research, I would have incorporated heating and molecular dynamics into this. And then the absorption spectrum for the iodine-doped nanowires has to be verified. And again, I talked about the density of states for the I-dopes. rectangular. That also has to be looked at because that didn't show the HOMO and LUMO states. And that concludes my presentation. Thank you guys.
Paper is open for discussion and questions. I can start. To which temperature you need to heat your sample in order to promote electron from HOMO to LUMO?
I'd say around 1,000 Kelvin.
Okay, then it's reasonable.
I have actually two questions. One is just based on your introduction where you were talking about doped, not doped, and P, responsive charge ions, selective charge ions. So what's the reason to dope? What exactly is the reason behind the doping?
We wanted to dope because the process of doping a material makes it a better material for semiconductors.
What's the physical reason? Right.
Okay.
Any physics behind it? What really makes it that material? What processes? What properties?
Okay. So basically, these thermoelectric materials have thermoelectric properties. So basically, the temperature differences between the junction where the wires meet makes like an electrical voltage, and that electrical voltage allows for electrons to pass through.
And what's the role of the doping?
It allows for that entire process to happen.
So this will not happen if there's no doping?
I mean, this will happen if there isn't doping. It's just that doping makes the entire process better.
And the second question is, so you were talking about thermoelectrics, right? But then you show in absorption spectra, and you talk about absorption of light. So I'm completely confused why light is involved in this discussion at all. Like why you need to absorb light with thermoelectrics.
Okay, so I did like 1-2 weeks of research on this. So basically, I just wanted to show you guys what research, all the research I had going into this. So
in other words, it's not really connected to thermoelectrics.
So just systematically study everything you can.
yeah.
Last question, but very quick.
So you want to study more with iodine dose system, but I'm just wondering why you choose iodine dose because the band can be very small, like 0.03 for it and starting moment becomes close value.
I'm sorry. Can you speak up?
You want to study more about iodine dose, but I'm just wondering why you interested on iodine dose because the band gap is very close. That certain momentum is also become close band gap, become matter.
It has to do with the KT efficiency of thermoelectric devices. The closer it is to the conductor, the higher the KT value can be in the thermoelectric device.
Very close to the KT value, like 0.03 electron volt, and also at 0.4 momentum band gap is close already. It becomes like matter.
Right. So, as I stated in my as you've seen in my density of stage graph, the IUD doped helical structure has a very narrow band gap. So for that reason, it's probably likely going to be ruled out as a thermoelectric material. But just for the sake of really verifying that, I plan to do more work with molecular dynamics on that structure, basically.
Okay, let's thank Kevin once again.